So nickel-based superalloys are are primarily used on gas turbine engines. Gas turbine engines possess many applications, such as jet engines in the aerospace industry, steam engines in the nuclear field, land generators to produce power, and boat engines in the marine field. These gas turbine engines also also contain low pressure, high pressure, and hot regions. And specifically in these hot regions is where the hot corrosion phenomenon is occurring. Okay, turbine blades in a jet engine experience many mechanical forces, such as creep, fatigue, and thermomechanical fatigue. And these turbine blades also operate in a high temperature environment where they are prone to oxidation and, of course, hot corrosion. Nickel-based superalloys are used to meet the extreme operating conditions of a gas turbine engine. Here we have a Rolls-Royce engine where the picture shows its materials composition. Near the inlet of the engine, it is mainly composed of titanium alloys, and near the top and bottom regions of composite material. Near the center of the engine here is steel and aluminum material, and most importantly, near the combustion chamber and exhaust of nickel-based superalloys. Nickel-based superalloys are very unique compared to these other materials because as its temperatures increase, they maintain their mechanical properties. And for this reason, they're used in these hot regions.
So some of the issues that we've that come across from this is the high temperature corrosion. So you have oxidation, which is the substrate reacting with the air, and sulfidation, which is the substrate reacting with the sulfur. And just quick definition, hot corrosion is the accelerated oxidation of a material at elevated temperatures underneath a thin fused salt film. In the picture here, you see two turbine blades. The blade here on the right has not been exposed to the hot corrosion, and the blade on the left has post-oxidation and has been exposed to the hot corrosion. And so here's our mechanism. This is how we believe things all come together to create this environment. So you have salt coming in with the inlet air when you're operating in marine atmospheres. The sulfur comes in with the fuel. The oxygen also in through the inlet air. And this all combines to form sodium sulfate. This salt, sodium sulfate, then reacts with the substrate, in our case nickel, to form nickel oxide, nickel sulfide. And this equation here is just showing you the nickel reacting with the salt to form sodium oxide, nickel sulfide. So a likely question would be, how do we combat this hot corrosion? First of all, we know we want to use a nickel alloy because of its mechanical properties at these high temperatures. And a perfect candidate would be nickel chromium, because the chromium would help prevent the corrosion. So like it says here, the chromium oxide layer will protect the substrate under these high operating conditions. And moving on now to our objective is to determine how much chromium is necessary to get the optimum protection to mitigate this hot corrosion. And we're going to do this by a mass loss experiment and electrochemical experiment. And here's just a phase diagram of nickel chromium. In the blue or on the y-axis, you see the temperature in degrees Celsius. The x-axis is the mass percent of chromium. And we'll be operating in the region outlined in blue at 900 degrees Celsius when mass percent of chromium from 0 to 25%. And it's the FCC phase of nickel. And our approach for this, like I said, would be immersion testing, which we're doing just small scale to kind of get more information and see how this all works. Then we'll move on to electrochemical tests, which will be a much bigger scale process.
All right, so I'm going to be talking about the experimental approach that we have conducted our experiment. And we have done this by performing immersion tests, which is a process on which nickel 200 specimens are immersed in sodium sulfate at 900 degrees Celsius for time intervals ranging from 1 to 25 hours. The way we do this is by, this is our nickel 200 sample, and we drill the hole through it so that we can place the aluminum rod through it, and we can suspend it inside the aluminum crucible. Following that, we build the aluminum crucible with the nickel 200 on it with sodium sulfate, and following that, we place the aluminum crucible with its contents inside the furnace and heat up the furnace at 900 degrees Celsius, and we let it sit there for time intervals ranging from 1 to 25 hours. Following that, we retrieve the crucible with its components from the furnace, and we retrieve and extract the sample from the crucible. And following that, we clean the sample so that we can remove the nickel oxide that is on the surface of the nickel 200 by brushing it and sonicating it. As you can see here from the pictures, after we retrieve the sample several amount of nickel oxide on the surface area of the nickel 200, and then after we have brushed it, some of the nickel oxide has been removed, and lastly, after we have sonicated, most of the nickel oxide has been removed. This helps us have more accurate measurements on the mass loss per unit area, and so we then, after we have removed most of the nickel oxide, we take several measurements to find the change in mass per unit area.
Here we have a mass loss per area versus square root of time graph in which our nickel 200 specimens were treated at 900 degrees Celsius. Plotted on the y-axis, we have mass loss per area in grams per millimeter squared, and plotted on the x-axis, we have square root of time measured in square root of hours. What we see is that there exists a linear relationship between mass loss per area and square root of time. So as the temperatures increase, the mass loss per area is also increasing. If mass loss per area were to be plotted against just time instead of square root of time here, we'll see that a parabolic relationship exists between the two. Okay, here we have a collage of microscopy images, where once again our nickel 200 specimens were treated at 900 degrees Celsius for time intervals ranging from 1 to 25 hours. Particularly looking at this microscopy image, you see at the very top we have a bake-like material, and at the bottom our substrate nickel. Between the bake-like material and our substrate, we have an oxidation layer, which we noted from this collage of microscopy images, that as the time is increased, the oxidation layer increases as well.
So to determine what was actually on our sample, what kind of oxidation was formed, we use X-ray diffraction. Here's a nickel 200 sample after a 100 run at 900 degrees C. On the y-axis, we have our intensity and counts, and on the x-axis, we have our diffraction angle. As you can see in the red, the peaks are characterized, or have characterized that nickel, which is our substrate, is shown. And then these peaks in green, I believe, is our nickel oxide, which is still there after all the washing. And it's important to note that these were done on the surface. These are surface tests and surface X-ray diffractions of our samples. And here's a nickel 200 sample after a 25-hour run at 900 degrees C. And as you can see, we still have our nickel substrate showing up and our nickel oxide. But now we have some peaks showing up that are kind of characterized by this nickel sulfide material. What we're hoping to show is that this nickel sulfide, as our as our hours increase, that we'll have higher and higher peaks of this. Now here we have a phase stability plot for sodium sulfate. On the y-axis, we have the log of the partial pressure of oxygen. On the x-axis, we have the negative log of the activity of sodium oxide. And here at the top, we have the log of the partial pressure of sulfur trioxide gas. And here, right in the center, is where our conditions actually form the salt. But as we raise the partial pressure of oxygen, we're going to peroxide or oxidize more the sodium samples, and as we increase the amount of sulfur in our conditions, we're going to create these sulfur-rich compounds. And here is our phase stability diagram for a sodium chromium sulfide and oxygen system. Once again, we have the log of PO2, the negative log of activity, and sodium trioxide. And right here is the oxide that is formed with the chromium alloying content in our nickel substrate. This chromium oxide is what we are looking to form to combat this hot corrosion phenomenon. Okay. So the addition of chromium to our nickel substrate, which you can see here, allows the gas, which protects this substrate from the gas, which is then diffused through the salt film, creating the nickel oxide layer. And then in these little crevices and cracks in the nickel oxide layer, the chromium will precipitate out and fill these cracks with a protective layer, not allowing further oxidation of the substrate. So here we have our chromate ions going to chromium oxide, forming 3.5 oxygen atoms and 2 oxygen ions.
So for our future work on the project, we'll be continuing with the immersion testing of the nickel 200. We'll begin immersion testing nickel chromium alloys with varying chromium content, and we'll be setting up an electrochemical test apparatus to determine the corrosion rate of the nickel chromium chromium using a tensiostat. Here is the electrochemical setup that we hope to model our next project after.
Alright, for summary conclusions, as I mentioned, we have conducted several immersion testings for time intervals ranging from 1 to 25 hours at a temperature of 900 degrees Celsius for specimens of A9200. From these runs, we have determined that as the mass loss per unit area contains a parabolic relationship with respect to time, and from our data, we have determined that there is an equation, which is the K value, which is the corrosion rate, which is -6 and 10 to the -5. With this equation, we can determine the change in mass per unit area for any desired time that we would like to analyze. As Brian mentioned, we also performed X-ray diffraction, from which we have found that as the nickel 200 is exposed on Na200 at 900 degrees Celsius, there shows that nickel sulfide is being produced. However, we're still in the process of determining whether as time increases, there is more nickel sulfide to be produced in the sample. And through optical microscopy, as Agustin mentioned, as time increases, the thickness of the corrosion surface is increased.
And so we'd like to thank